Okay, in this video, we're going to talk about cost estimation, chapter 8, and I'm going to divide it into two videos, the high-low method and regression in the first video, and then learning curves in the second video. And before we get into the actual how-tos of this, um, understand why we use cost estimation, primarily for two purposes. One is so we can create budgets for the year, a quarter, month, whatever it might be. But budgeting is an important concept in business, and while the budgets actually fall on management, it's the accountants who often put those together. But management is always responsible for the budgets. The other thing is more of a sales function, which is for us to be able to prepare bids. And the two elements of this, of course, we're going to use high-low and regression here in this video. We'll use learning curves in the other one. Learning curves are used more for cost estimation when we're doing a new task, something we haven't done previously. And so we can run a few operations, do it about 8 times, and we can figure out a learning curve is an exponential curve, and we can figure out what the decay of time is. When I say decay, that's a good thing, right? The how much faster we can do something over time when we learn it. And so when we get that, when we get the exponent for that, we can then estimate what our time will be. And of course, time is money in business. So that's the value of learning curves. Very useful when we're bidding a project like government bids where nobody's ever done what we're about to do before, those sorts of things. And so we know it's technologically feasible. We just don't know how long it's going to take us to do it on a large scale. So let's start then with exercise 8-3, cost relationship. We have chimney sweeps provides cleaning services for residential chimneys and fireplaces. The cleaning service requires $35 in variable costs for cleaning materials. The fixed cost, labor, company's truck, and administrative support is $165,000 per year. Chimney sweep averages 100 service calls per month. So there are two ways you can approach this problem. I'll show you both. This is 8-30. The first way is my preferred way, which actually will lead us into chapter 9 a little bit. And that is, we have the $35. So we're wanting to know what is the average cost per cleaning. So we've got a variable cost equal to $35. And then we've got a fixed cost, which is 165,000. And that's going to be divided by 100 calls a month, but then there's 12 months in the year. And so that's $1,200. So 165, 1,200 is 137.50, and we get 172.50 for that. Okay, so the other way you can do that is to put it on an annual basis. So we'll take the variable cost equals 35 times the 1,200, which we just calculated above. That's how many calls we have. So 35 would be 42,000. And then the fixed cost is given to us at 165. and that's going to give us 207,000 there. We then divide that by the 1200. And that'll give us 172.50. So, mathematically they're equivalent, but it's just which way you approach it. Do you want the total cost? Do you want the per unit cost? I can see advantages to working it both ways, but that'll get you your answer on that. Okay, then number 8-33. We've got cost estimation using the high-low method. Lawson Advertising Agency is trying to persuade Kansas City Sale Boards Company to spend more on advertising. The agency's argument is that a constant, strong, positive relationship exists between advertising and sales in the sale board industry. Sue Lawson presents these data taken from industry data for stores similar in size and market share to Kansas City sale boards. And so I'm not going to print those all off. You can see them here. And it says we use the high-low method to estimate the relationship between increased sales and increased advertising sales. So what we have here is the independent variable is advertising expense. This is the activity that we want. This is the revenue that we're seeking to find out how it's correlated with. So when we do that, we always look at the high and low activity. The high activity is 5,500 here. The low activity is 2,500. They've put those in order for us, and then you can see we use the costs that are associated. Now, in this case, it works out that the high expense and the high sales, the high result, occur in the same period. It doesn't always. You always use the high activity level to judge high-low, and then the cost associated with it. It's entirely possible that the high activity is not associated with, in this case, the high revenue. But in this case, in this particular case, it is. And so we set that up. And this is just solving for a line back to 7th grade algebra, if you will. We know that we have a point at 5,500, and the y-axis is 150,000, and we have a point at 2,500 with an associated 9,600 on the y-axis. So we get, the first thing we do is we find the difference in those. So this is going to be 3,000 difference in activity level, and this will be 54,000 difference in revenue. All right, and so we want to find out the relationship there. So we just take the 54,000, the change in result, divided by the 3,000 change in activity. And that gives us $18. So every change in advertising revenue results in $18 in sales revenue. Now we can go back up to here, and we can use either formula. It doesn't matter, or either point, and and I'll do both of them to prove my point here. So we know that the total cost is 150,000, and we know the variable the variable there is minus 5,500 times 18, and that equals, this is going to be our constant here. So 5,500 is 99,000. So 150 minus 99,000 equals 51,000. So our formula for costs becomes 51,000 plus 18x or 18n, the x in this case being the sales dollars. Okay, let me go ahead and plug it into the other formula just to prove that it works. Either formula, either point that you choose, it will be 96,000 minus 2,500 times 18. So 2,500, 18 times is 45,000. So 96,000 minus 45,000 equals 51,000. So it doesn't matter which one we use, we're going to get the same result. And so our formula ends up being the same on that. All right. So that's that's using the high-low method. It then asks us to graph, and we see that, you know, what you would have here is a graph that starts at 51,000 and then goes up for every dollar in sales. It goes up $18. 18 is your slope here. So that's what that looks like. And then it says, does the data prove Sue's point? Well, yes, it does. What it doesn't prove is, which we'll get to in the next chapter, is the advertising worthwhile for that? All right, so that's exercise 8-33. Let's move on then to 8-34. This is a regression analysis. Wang Manufacturing uses regression analysis to predict manufacturing overhead costs based on direct labor hours, machine hours, and has developed the three following regression equations. So we see this. Okay, so this is a regression output, and you can do, actually Excel does excellent regression. There's absolutely no problem. It's a very powerful regression tool. A lot of people here at UTPB use SPSS, which is a statistical package for social sciences. I personally use SAS, Statistical Analytical Services. The reason I use it, you can do a little more programming in SAS, and so you can manipulate your data a little bit more. But in this regression analysis, the first thing you always want to look at is this R squared value. Now on this one, they don't have, but I'll show you when we do the next problem. Well, actually, I'm going to do a takeoff of the next problem. But you want to look at the R squared. So clearly, regression 2 is clearly inferior. 0.58 to 0.55 is not a whole lot of difference there. But we also can look at the standard error. The standard error is larger. You want the smallest standard error. So if we were just looking at only the standard error and the R squared, you would say regression 3 is probably the best predictor. This R squared coefficient of conformance, tells you what percentage of the output is estimated by the model, which then you get how much is an error on that. So with regression one, we say 55% is estimated by the model. Regression two, we get 58%. What's good, what's bad, just depends on what you're trying to model. In something like construction, you can get an R squared up in the 90%, 0.9. R squared is always going to be between 0 and 1. So you can get 0.9, 0.92, 0.95 is not uncommon in something like construction. On the other hand, if we're doing statistics involving humans and human nature, if we get 0.35, we're explaining a lot of how people behave. So it just depends on what you're trying to explain, what a good number is. Um, just various things. But so we've got these two that are pretty close here, 55%, 58%. So then we go down to the t values. The higher the t value, the more correlated the numbers are. Ideally, t values should be above 2. And we can see regression one. So regression one uses just direct labor hours. Regression two uses machine hours, and regression three uses both direct labor hours and machine hours. So what happens what it's telling you when you get this low t values on a on multiple independent variables is that there's something called multicollinearity. Well, it's it's big word that simply means that the two have a relationship with each other. Okay, what would be a high multicollinearity? Um, try to think of something here. Let's say that um, something like the heat um, and the season and water park sales. Well, there's a high degree of correlation between heat, the summer heat, and the season. Summer months, June, July, August. Um, so it doesn't really, you know, adding a variable, as you can see in this case, adding a variable only explains 3% more. So if I were choosing, I would choose regression one. Um, just because you're not that. Now, in other regressions, there will be an additional line here. It's usually right below the R squared line called adjusted R squared. It's in your Excel output, it's in your SAS, SPSS output. And this adjusted R squared takes these into account. And so you can actually end up just looking at the adjusted R squared and having a good feel for whether you do that. One of the when I have the face-to-face classes, one of the things that I do is I take something, that has a pretty obvious correlation, like number of windows in a building and the building cost, because number of windows is going to talk about the complexity. It's also going to talk about the size of the building. So those things are going to be correlated. And so we run a regression and you get an R squared, and it'll be, pretty high up in the 80s, something like that. And then I'll go around and ask each um, member of the class their birth month. And, so we put it like if you were January 16th, it would be 0116, your birth month and day. So 0116, May 5th would be 0505, right? And I put that in as a number for the number of observations that we have on these windows. And your R squared will, I've only had it not go up once, and I've probably done this dozen, 15 times. Um, and, you know, obviously there's no relationship um, between the students' birth dates and the cost of a building, and so you know that's unrelated to that. So, you know, you get funny results like that when you plug in data, and that's why it's better to look at the adjusted R squared on that, or the look at both the R squared and these T values on that. So that's number 34 pretty much on that one. Okay, so number 35, this one gets a little bit involved. The first part's pretty easy. So we've got the high-low estimation for residential homes and offices. So we've got the month is not going to be important. Now, months may become important if we get into time series, but we're not getting there. In this class, your chapter has one little paragraph on time series. I don't think it's worth getting into. Um, but we're going to do the high-low method, and then this problem doesn't call for it, but I'm going to do the regression on this same data, um, and show you the Excel output on that. So anyway, so we've got the machine hours and the maintenance costs. So what we're wanting here is to is the activity level is the machine hours. So we're going to look at the high machine hours. So 1880 looks like the high there. And then we need the low. I don't 1410 here. Is that the low? That's the low. I see there. Okay, so then we set that up. We're going to have 1880. Let me change pins. We're going to have 1880 is our high activity level, which is machine hours, and that is associated with a cost of 3,005. And then our low that we determine is 1410, and that's associated with a cost of 2570. So just like we did before, we're going to find the difference in these, 470 here. The difference here is 435. So then we get we figure the change in cost per change in activity level. So we've got 435 divided by 470. And that's going to be 0.92. I'm going to say 6. I'm going to round it up. 553,926. Again, we can plug this back into either formula. 3005 minus 1880 times 0.926 equals 1740. And so we get a constant of 1,264 and 12 cents. I can plug this back into the lower one, and I get 2570 minus 1410 times 0.926. And we get 1264 and 34. The difference here in these two is the rounding that I did here. If I put that out to 552, it would have come out a little bit closer, but this is obviously this is close enough. This is going to be an estimation. So our formula for the cost is going to be a fixed cost of 1,264, and take your pick, 23. That's halfway in between, plus the activity level times 0.926. And that will be your cost formula on that. All right, so the next thing that this one asks us to do is calculate the MAP, M-A-P, and that is the MAP on that is the absolute percentage error, okay, on that. So what we have to do is on this, we have to get a estimate for each level here now. And I'm going to do that in Excel because I've already got it up here for the let me see if it will capture the Excel here. So I got this up here for your regression. Again, here's our activity level. Here's the thing. So I'm just going to plug in the formula with the activity level. And so that's going to equal, and our formula is $1,264.23 plus, and we'll do the parenthesis, 0.926 time, because times in Excel is the asterisk. This, close the parenthesis, and you see we get the estimate. And so we just pull that down. And so this is our estimate here of what the cost was. Here was the actual cost. And so, so what I'm going to do is in this column, I will take the equals this, the actual, minus this, enter, and we get the error. Okay, so now what I do with that is I can, the MAP is going to call for the absolute error. So now I think I can sum this up. It's been a while since I've done this. Sum absolute. Try it this way. Okay. L4. There we go. Okay, so now I pull that down. And so I've just changed those all to absolute values. And now I just sum those up. Oops. And so that's our MAPE on that is the 755,024. Kind of doesn't show real well for you there on the Excel. That's unfortunate. So that's how you calculate the MAPE in Excel. And then I want to take this same problem. I'm going to delete what I just did there. I want to take this same problem and show you how to do regression. So have it on data, go to data analysis, and we want to do regression. Oops, go over here so it shows up. Click on regression, hit OK, and you get the Y and the X range. The Y range is what's called the dependent variable. It's what you're trying to predict. The X range is the independent variable you have there. Okay, and let's see, we'll do some label, and I'm going to put it in a new worksheet. And hit OK. And you see we've got a new worksheet, and I'm going to widen this out. One of these days I'll figure out how to do Excel in these videos without just having a picture of Excel. As you can see here, we've got the R squared and the adjusted R squared on this. That takes into account things. And so we see that's the regression. We see the intercept, so 1769. And we see the slope is 0.611, and so it's quite a bit different than what our high-low method gave us, and that's normal because we're using a lot of points versus just the 2 points. Now let me tell you about regression. It is mathematically the best estimate you can get using historic data. Now, obviously, let's say you're trying to forecast your heating costs for next year, and you've got last year's heating costs, and you've got the average temperature for the month, and you've got the amount of natural gas used to heat your building, and you've got the cost of the natural gas. And one of the things is natural gas tends to be a little bit cyclical, not as much as it used to be, but tends to be a little bit cyclical. And so it goes up in the winter, goes down in the summer, is the traditional thing that happens on that. And so you estimate your cost. Well, comes along and you find out that that the cost of natural gas from last year doubled. Well, you can calculate the amount that you expect to use using regression, but you're going to have to change the cost because you know that something's changed in your inputs, right? So just understand what the limitations are on regression. Regression is a wonderfully powerful tool. Excel does a great job of it, but just understand what the limitations are. Again, there's our data, and there's our output there. So there are coefficients there. So our formula would be 1,769 plus 0.617 n or x. All right. So that's the regression on that. Okay, so that's what I wanted to talk about, high-low method and oh, let me go back one more thing about the high-low method. A couple of things that might happen here. So this is our data from before using the high-low method. We did that. What happens? And I haven't seen it in this book, but what happens if you have, like here, let's say you have two machine hours that are the same, either the high or the low are the same. And if that's the case, um, you just take those and average the cost. You use the high that's tied, but then you average the costs for a number. That helps out. One of the things that they talk about in the book is you want to plot your data. And one of the things that you look for when you plot your data, let me go ahead and draw this out. So your data looks something like this. It's not going to follow perfectly, right? The more linear it looks, right, the better your R squared is going to be. On the other hand, if you have something that looks like a giant fuzzball, right, it's all over the place. It's kind of hard to draw a line through there and say that's it. Whereas on this one, it's pretty easy to say, gee, it follows a trend that looks like that, right? I'm a little bit off. It should be shifted a bit up there. But so, this is one of the reasons that you want to graph your data because you're going to get an idea. This is going to have a low R squared. This is going to have a high R squared. But the other thing that happens is you're going to get numbers like this, and then you'll get something here, or you'll get something down here. Those are called outliers, and how you treat outliers depends on what you're trying to accomplish, right? The first thing is I try to explain outliers. Okay, our costs were really low, even though this is our activity on the x-axis, and here's our costs. Our activity or our costs were really low, even though our activity was high, because we caught a supplier one of our suppliers in a going out of business sale, and so we were able to get some supplies on the cheap that month. Okay, that explains that. That's probably not going to happen in the future. Let's throw that out, right? On the other hand, the outliers are where the interesting things happen. This is what could go wrong, right? Why did it go wrong? We want to be able to explain that. This might be how we can improve. It might not be the supply. It's like, we just had a bunch of factors cobbled together. How can we repeat those? Um, you know, business um, business is notorious for making small little gains over time, right? We're 3% better this year than we were last year. We're 2% better than the year, that next year than this year. Those are all great, but if we can make big gains, that's where you're going to do things. But big gains are difficult. Uh, if you listen to the public, like people like Peter Diamantes and stuff, and I love their futurism. Don't misunderstand what I'm saying here, but they always talk about 10xing things and moonshot programs. That's great, and when you can pull that off, you get very, very wealthy. Think Microsoft, think Facebook, think Apple, right? Um, think Tesla. So when you can pull off these, big major disruptions to the way we do things, but that's not where normal business resides. Most of the time we're looking for 2-3% improvement in efficiency each and every year, and when we do that over time, we get better and better and better. So just take that into account when you're doing those sorts of things. All right, so that's going to take care of us for this part. And then the next video, we're going to talk about learning curves.